Even while making this video, I can tell that you can probably tell that this video is shorter than the rest of my videos. And that is because it is not a real video, it is just a bonus video to my last video, which was about summations. And I just wanted to have a little bonus problem here. Now, unlike my other problems, this is not a normal problem, you can call it. This is actually a proving problem. Now, I'm going to draw out for you something called Pascal's triangle. Now, this is probably not something new to you. This is something that is shown to a lot of elementary school kids, and finding patterns in Pascal's triangle is something of a puzzle, like a math puzzle, if you know what I'm saying. So first, draw a 1 at the top, and then 2 1s in the row below it, and then 2 more 1s on every edge on every row. So I'm going to draw, say, 6 rows. So in between 2 numbers here, you have to write the sum of the 2 numbers above it. So for example, 2, 3, 3, 4, 6, 4, 5, 10, 10, 5. But then one thing that you might not notice is that every term here is the row choose the leftmost position of it. So if that's a bit confusing, this is row 0, this is row 1, this is row 2, this is row 3, this is row 4, and this is row 5. This diagonal is position 1, this diagonal is position 2, this diagonal is position 3, this diagonal is position 4, 5, 6, and so on. So each value here is the row number choose the diagonal number. So for example, if you have this one, for example, the 3 here, this is row number 3, and this is spot number 0, 1, 2. So the value 3 is equal to 3 choose 2. So to those of you who are unfamiliar with what choose means, n choose k is equal to n factorial over k factorial times n minus k factorial. This is equal to 3 factorial over 2 factorial 1 factorial, which is equal to 6 over 2, which is equal to 3. And 3 choose 2, row 3, position 2. But now I'm going to get into the problem. Now the problem, you see, is to prove that the sum, yes, of n choose k is equal to 2 to the power of n. You should prove it by induction. Alright, and now I'm going to solve this problem. Now first, as I said, I'm going to prove this by induction. For those of you who don't know what proving by induction is, it's 3 simple steps. The first step is that I will prove that this is true for k equals to 0. The second step is I will assume that this is true for all values. It might not be true, but for now I'm going to assume. And then I will show that this works for n plus 1. By showing that it works for n plus 1, I show that it works for 0 plus 1, and then 0 plus 1 plus 1, and then 0 plus 1 plus 1 plus 1, and so on. So therefore, I have proven this value true for all integers by proving by induction. So the first step is to prove that this is true for 0. So it is quite obviously true that taking the sum of 0 choose k is equal to 2 to the power of 0. Now you see, since it starts at 0 and ends at 0, we can pretty much just erase the summation and then just write a 0 here. Now 0 times 0 is equal to 0 factorial over 0 factorial squared, which is equal to 1 over 1, which is equal to 1. So 2 to the power of 0 is also equal to 1. And so we have proven the first step. Now this is true if n is equal to 0. Next, we need to use something called Pascal's identity. Now I need to show you that k plus 1 choose n. Actually, it should probably be n plus 1 choose k to avoid confusion is equal to n choose k minus 1 plus n choose k. And now you're probably wondering why I showed you Pascal's triangle earlier. Well, this is when it comes in handy. Now, it's pretty easy to prove this algebraically, but I'm going to prove this visually. So I'm going to draw Pascal's triangle. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Now, if I have row n plus 1, and then the diagonal k, so say I choose 6 here. Now, if I take the row above it, I will get this row over here with the 1 through 3, 1. Now, choosing the same diagonal as it puts it to the diagonal above it. So we take this 3 over here. and then the one to the left of it would be diagonal k minus 1. So we also choose 3 over here. Now it's pretty clear to see that 3 plus 3 is equal to 6. And by definition of what the Pascal's triangle is, this is kind of just true. So this kind of has already been proven by the existence of the Pascal's triangle, which is why it's called Pascal's identity. Next, I also want to prove two a little bit more trivial things. So it's true that n choose 0 is a constant. It is true because in diagonal 0, everything is 1 by definition of the Pascal's triangle. It is also true that n choose n is a constant. For the same reason why n choose 0 is a constant. Everything along here is a 1 and everything along here is a 1. So both of these must be constants. So now, let's get into the second step. If we write out the sum above here, we will get n choose 0 plus n choose 1 dot dot dot, and then n choose n minus 1, and then we add n choose n. So we've already assumed that this is true because we're trying to prove by induction. But consider what happens when we take the case of n plus 1. So now we have n plus 1 choose 0 plus n plus 1 choose 1 plus n plus 1 choose 2, and so on until n plus 1 choose n plus n plus 1 choose n plus 1. So notice that by Pascal's identity, n plus 1 choose 1 is equal to n choose 0 plus n choose 1. So n plus 1 choose 1 is equal to n choose 0 plus n choose 1. Similarly, n plus 1 choose 2 is equal to n choose 1 plus n choose 2, and then so on and so forth until we get n choose n minus 1 plus n choose n. But what we are left with here is n plus 1 choose 0 and n plus 1 choose n plus 1. Now you see, both this and this can be converted. You see, since anything choose 0 is a constant, we can set this to be equal to n choose 0. And also, we can set n plus 1 choose n plus 1 to n choose n. So combining all these terms together, we have 2 n choose 0s, 2 n choose 1s, 2 n choose 2s, 2 n choose n minus 1s, and 2 n choose n's. So in the end, we get 2 times n choose 0 plus n choose 1 plus n choose 2 dot 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 plus n choose n minus 1 plus n choose n. Multiply all of this by 2, of course. But then, we've already shown that it is true that this in the brackets is equal to 2 to the power of n. So multiplying 2 times 2 times 2 to the power of n is equal to 2 to the power of n plus 1. And now we've shown for n plus 1, it is equal to 2 to the power of n plus 1. So this holds true for n plus 1. And so induction is done and we have proven the statement. Alright, thanks for watching. Hopefully you enjoyed this little bonus proving video, and see you next time.